Okay, calculus lesson 3.7, optimization. A square piece of cardboard has side lengths of 10 inches. When squares of equal size are cut from each corner, the cardboard can be folded to form an open box. Find the max volume of an open box. So optimization, that means we're going to be finding maximum and minimums. And we need to write an equation first in which to do that. So we have a square box. Or a square piece of cardboard rather, and we are going to cut equal lengths, corners of equal lengths out of each side, each corner. Okay. And each side here is what, 10 inches? Okay. And we don't know what these corners are right here. So we're going to call that X length, because these are squares. That's X, this is X, this is X. We don't know the dimensions of these little squares here, but we do know that they're equal squares. Okay? And what we want to do is we want to take that and we're going to take these little squares when we cut them out, and we're going to fold this up and make an open top box. So, open top box here. Our box is going to end up looking something like this. Okay, so here's our box. And what we did is when we cut these corners out right here, we folded along these dotted lines here to make this box. So when we folded this edge to that edge, what we ended up with was actually a height right here of X. All these little heights right here, they're all X. So that meant that the length and the width of this box changed, of this cardboard, because it was 10, but I took X from here and I took X from here, so that left me with this length right here of 10 minus 2X, and the same thing happened here because this was 10, that was X here, that was X there, so I took 2X away from that length of 10. So what I end up with is that the length and the width are 10 minus 2x, okay? And you did problems like this back in Math 3 and in Pre-Cal as well. But with calculus, we do it with what we refer to as a primary and a secondary equation. And the primary equation is the one that we are going to differentiate in order to find the maximum volume. Okay? So the way that we do this is our secondary starts with what we know. We know that we have a two-dimensional piece of cardboard, and if we wanted to know the area of a two-dimensional rectangle, we would use area equals length times width. But our primary equation is the one that we're going to differentiate, and we want to differentiate volume. So we want a formula for volume. So that is volume equals length times width times height. Okay? Technically, you can do this without a secondary equation. You could just go ahead and plug in your length and width and height right here. But I want to show you how to do it with a secondary equation, because sometimes you get multiple choice answers. Questions on the AP test, and they want to know what you know about the secondary equation. So your secondary equation actually comes from where you start. Well, you start with the square here, and again, we know the area of our square is length times width, or side squared. Well, one side of our box is going to be 10 minus 2x, so we're going to square that. And that is your length times your width. So I'm going to take this and put it here. Okay. And so I'm going to put 10 minus 2x quantity squared right there in the place of length times width. And then my height is going to come from right here. The height of that box is x. So I am going to put that there. And that gives me my primary equation that I'm going to differentiate. Alright? And again, like I said, this is just really a Math 3 problem. You did stuff like this in Math 3 where you found that volume equation, and then you actually would put that in your calculator and you would go to second, calc, maximum, and you'd find the maximum point. But now you're going to do it with calculus instead, because that's what we do in calculus. We do all the algorithms that your calculator is programmed to do. So we are going to differentiate this function right here to figure out what that maximum is. So we are going to do the derivative of volume with respect to x. This is going to require chain rule and product rule. So I'm going to keep the 10 minus 2x quantity squared, differentiate x, plus differentiate 10 minus 2x quantity squared by bringing that 2 down in front, bring down the 10 minus 2x, decrease that power by 1, and then take the derivative of the inside, negative 2x. So there's my derivative, and then I'm going to of 10 minus 2x quantity squared, and now I'm going to keep the x. So I'm going to clean this up a little bit. That's going to be 10 minus 2x quantity squared. And then all of this right here is going to become negative 4x squared times 10 minus 2x. And I am going to now factor out of this term and out of this term. I'm going to factor out that 10 minus 2x that shows up in both of them. And so here I'm left with 10 minus 2x. And then up here, I am left with actually just a negative 4x because Ms. Letchworth made a mistake right there. The derivative of 10 minus 2x is just negative 2. Let's fix that. There we go. Okay. So 10 minus 2x minus 4x, and now my derivative of volume with respect to x is 10 minus 2x times 10 minus 6x. Okay. To find a maximum, remember you've got to find where the derivative is equal to 0, as well as where the derivative does not exist. Oops, so I just got it out of my mouth to set that equal to 0, didn't I? There we go. So if I set this equal to 0, then I've got 10 minus 2x is equal to 0, 10 minus 6x is equal to 0. Here I am going to get that x is equal to 5, and here I'm going to get x is equal to 5/3. Okay? Now before you keep both answers, think about your domain for this problem. Can x be these numbers? Well, if you let x be 5, and you put 5 right here, you have no length, you have no width. Okay? So, because that gives you 0. The 10 minus 2x, when x is 5, gives you 0, right? I mean, you just figure that part out, okay? So I can't include that. That is not in the domain of my problem. It may be in the domain of that polynomial, but in respect to that problem, in context of the problem, 5 cannot be in the domain. So it's the 5/3 that we're going to keep. And we're only going to keep it after we test it. Okay, so I'm going to come over here and I'm going to make a little sign analysis for the derivative of my volume, v prime. And again, think about what your domain is. Okay, volume can only be, your derivative of volume can only go to from 0 to 5, not including either, so it's open. But the reason why I'm leaving this left endpoint as 0 is because it would be crazy to let x be anything that's negative here, okay? Because x is your height, and height can't be negative. So the domain that I'm working with is from 0 to 5. And I'm going to test out 5/3, which is the same thing as 1 2/3. Okay? So if you use a test point on the left side, then you get a positive. And if you use a test point on the right side, you get a negative. So that means that this is definitely a maximum because this changes from increasing to decreasing. So now that I know that 5/3 is my maximum, all right, then I'm going to go back and read the problem. I'm like, well, what am I supposed to do with 5/3? Well, it said find the maximum volume of the open box. It didn't say find the X value that gives you the maximum volume, okay, which is what X is. That's what 5/3 is. It says to actually find the maximum volume. So that means I need to go back to my volume equation, 10 minus 2x quantity squared times x, and in the place of x, I need to put 5/3. I'm going to put that x in front, so I'm going to do 5/3 times 10 minus 2 times 5/3 quantity squared. So that's going to be 5/3 times 10 minus 10/3 quantity squared. 10 is the same thing as 30/3 minus 10/3. So that's going to be 20/3 squared. 20/3 squared is 400/9. So that right there is going to give me 2,000/27. And this is volume, so that would be cubic inches. If you had access to a calculator for this problem, then you can change that to 74.074, but like I always advise, try to do these without a calculator because you never know. So if you're given two numbers, the sum of the first number squared and the second number is 27, find the max product of the two numbers. So we have two numbers. X is one number. Let's say the first number. And y is the second number. Then we need a primary equation and a secondary equation. And the primary is going to be the one that you differentiate. Since it wants to know the max product, then it's going to be the product of x times y is the one that we're going to differentiate. And the secondary is going to come from this, the sum of the first number squared and the second number. So your sum is equal to the first number squared, x squared, plus the second number, y. We want to differentiate that one. Now when we differentiate, we just want two variables, and right now we have 3. So your secondary equation is going to help you to get your primary equation into just two variables. So I'm going to take this secondary equation, and I'm going to solve one of them. I'm going to solve it for either x or y. Okay? I don't know which one. It doesn't matter which one. I'm going to solve it for y because y is easier. It's not squared. I do know that my sum is 27, so I'm going to put 27 in the place of s before I solve this for y. And once I solve this for y, then I get that y is equal to 27 minus x squared. So now if I put this here in the place of y, then I now have p in terms of just one variable instead of two. So whatever you're going to differentiate, you just want in two variables here. Okay? Now I could use product rule here, but I think I'm going to just multiply everything out and use power rule. Oh, no, I'm here today. Okay. Alright, so p equals 27x minus x cubed and I'm going to get the derivative of the product with respect to x, which I can write it as dp dx, or I can write it as just p prime is equal to 27 minus 3x squared. Set that equal to 0. Solve for x. So I get x is equal to plus or minus 3, and now I'm going to do a sign analysis on this one to figure out which one is my maximum, because that's the one I'm looking for. So I put negative 3 here, positive 3 here, and my sign analysis ends up being negative, positive, negative. So 3 is my maximum. See, if the problem had asked me for my minimum, I would choose negative. So x equals 3 is what gives me my max, but it actually helps me to find my max product. So I'm going to go back to P, which was x times y, and multiply 3 times whatever y is. So I don't know what y is. That means I've got to go back up and figure out what y is. So y is 27 minus 3 squared. So that gives me 18. So my maximum product is 54. Okay, number 3. So you have 500 feet of fencing to make a rectangular pig pen using the barn as one side. So it's a rectangular pen. Let me get my rectangle drawn here. And one side of the pen is going to be the barn, so I'm not going to put fence there. I'm only going to put fence around these 3 sides right here. And that's going to be 500 feet. It's going to go around these three sides. So again, I'm going to have a primary equation and a secondary equation. So it wants to know what is the max area. So my primary equation is going to be length times width. My secondary equation, well, when you put up feet of fencing around a rectangle, that refers to perimeter. So they're giving you information about the perimeter, so that's going to be your secondary equation, which is only going to be 2 times the length plus whatever the width is. Not 2 times the width, because we're not going to use that side. Okay? So I know that my perimeter is 500. So my perimeter is 500. And it's equal to twice the length plus whatever the width is. I want to differentiate my area. So I need that to be in terms of just one variable here. So I'm going to solve this one for W and put it right here. And then this is going to be the one that I differentiate. So I'm going to multiply that out. Area is equal to 500L minus 2L squared. So the derivative of area with respect to x, also known as a prime, I don't care which one of these you write, is 500 minus 4L. And I'm going to set that equal to 0. So 4 times the length is equal to 500. So that tells me that my length is 125. So we got the length is 125. And what did our problem ask us to do here? It asked us to find the maximum area. So to find my maximum area, I got to know width. So now that I know that my length is 125, come back up here and figure out that the width is going to be 500 minus 2 times the length. So that's going to give me 250 for my width. So that means my maximum area is going to be my length times my width. So my maximum area is going to be 31,250 square feet. So number 4, determine the dimensions of a rectangular solid with a square base that has a max volume if its surface area is 337.5 centimeters, and that should be centimeters squared because area is always centimeters squared. Oh, there's my square. I thought that was a question mark. Okay, so let's draw this. We got a square base. And it is a rectangular solid. So I'm going to draw both of those bases to be equivalent here. This may or may not be pretty. Let's see, it's pretty enough. Okay. And I'm going to dot part of this solid that I cannot see from my perspective. There we go. Okay, so if I have a square base, then that means that the length and the width of the base are going to be the same. I'm going to call this both x, and my height is going to be y. So determine the dimensions of the rectangular solid with a square base. So I've got to have a primary and a secondary equation here. I want the max volume. That's the one I'm differentiating. So that's always your primary. That would be length times width times height. And the surface area is your secondary. So your surface area would just be the sum of all 6 of these spaces. Well, this bottom right here has a surface area of x times x. Well, that's the top is the same, the bottom is the same thing as the top. And I have 2 of those, so that's 2x squared. And then this side right here is this side right here. One side would be x times y because that's y, that's x. So one side is x times y, but there are 4 of those. So that's how you get that equation. Put it all in the same color. So this was my 2 bases. They were x squared each, and my 4 sides were x times y. So that's my area right there. Okay. Now I know that my surface area is 337.5, and I'm going to solve that for y because it'd be easier to get y by itself. You can solve for x or y. Y is just easier. That equals 4xy, and divide by 4x. And so this is what we get for y. Okay. I'm going to put all of that over here. So I'm going to rewrite volume as length times width times height, x times y. That is x squared y. And I'm going to put all of this in the place of y right here. So there's my x squared times my y. And I'm going to simplify that quite a bit before I differentiate. I'm going to divide this x into that one. And I'm going to factor out this understood 1/4 as a scalar. So 1/4 x times 337.5 minus 2x squared. So that would be 1/4 times 337.5x minus 2x cubed. That's going to make it easier to differentiate. So my derivative for volume is going to be 1/4 times 337.5 minus 6x squared. So when I set this equal to 0, I'm really just going to have to set this part equal to 0, because that's the only factor that has an x in it. And you divide both sides by 6, 56.25, and you get that. When you take the square root, you get the x is plus or minus 7.5. Okay, now your domain for this problem, because it's volume is not going to be negative. So our sign chart is going to be open at 0. So now I can go past that, and we're going to evaluate the sign chart on 7.5. This becomes positive, this is negative. That means that this would definitely be a maximum. And the problem is asking me for, look again, the maximum volume. Okay, right now I have the x coordinate that makes that the maximum. So what I need to do is figure out, well, what is the y coordinate? And then I can multiply together and figure out what that volume is. So if this is my x, then I can just plug that back into this formula right here to figure out the y. Okay, and that tells me that that is also 7.5. So my volume is x squared times y. So that would be 7.5 squared times 7.5. So my maximum volume is going to be 421.875 cubic centimeters.